I expect that we should probably select our topics, what each of you would like to pursue a little further by 2 weeks before the end of the term. And so you have adequate time to prepare your material. So, Red, over this coming weekend, I'll send out all this information that I just kind of haphazardly threw at you. And then I'll ask that in I'll try to make it in roughly a week and a half time that you propose to me some topic that you would like to do for the final project. And then we can discuss further, and hopefully I can provide you some resources to set you off in a direction that might be helpful. Okay? So that's what we're looking at, more or less. Now turning to the midterm, how is the practice exam going? I realized I made a mistake because I asked you to compute residues, which is not a term we explicitly went over in class. That's because I had originally had a problem that defined residues and asked you to compute them on problem set 3. But in my final draft, I omitted that problem. So I'll send out the solutions to the midterm exam shortly after class. But other than that, is the difficulty manageable? It seemed okay, generally. Modulo looking up the definition of residue. No? Is that okay? Okay. Okay, good. So yeah, this is again roughly what you should expect on Friday when we have the midterm in class. I don't expect that any of you will have too much difficulty.
The topics won't be the same, right? Or
well, what do you mean by that?
like, is the midterm translatable to, or the practice exam translatable to the midterm in the sense where like it's gonna be the same topic, but like not necessarily different numbers, but some other variation of that specific. I can't think of any of the problem sets right now. Right?
Yeah. So
it won't vary too far from like the different chapters like that are presented in this.
well, so the practice exam is just chosen from the material that we covered,
Yeah.
essentially at random, right? Likewise,
Okay.
for the actual exam.
Okay.
Yeah.
Was there anything on any of the problem sets that we didn't cover in class that might be in the midterm, like the tag residue would have been?
State your question one more time, I'm sorry.
So you said like you were originally planning on having residue in the third problem set, which is why it was on the practice midterm. Is there anything else that was only on the problem sets that we might see? I can't really think of everything that we did on the problem sets right now, but.
Possibly.
Okay.
I'll say possibly. Right. You should have some familiarity with everything that we've done in any capacity. But nothing that will be too hard, and don't worry, I'll make sure that the actual exam only refers to terms that we've actually discussed. I'll admit, the last problem also, I gave you some definition of what a homogeneous degree 2 polynomial is, right? It's just a polynomial of more than one variable where the sum of the powers of each variable for each summand is 2, right? I won't do anything like that on the actual exam. I guess I was too ambitious or wanted to take that as an opportunity to give you some more exposure to things. But the difficulty of the problem, the actual mechanisms that you use to solve it, are things that we've traversed fairly well. Right? Okay. Good. Any other questions about the test?
Do you have any recommendation as to how to study other than doing the practice exam and then going over notes and problem sets?
No, I think that will be more than sufficient.
Yep.
Yeah. I mean, if you want, you can try some problems from the book that weren't assigned, and of course, we can discuss those if you have any questions about the solutions therein. But yeah, I think looking over everything that we've done should suffice.
Did you create all the problems yourself? Or are they like inspired from books or?
I have no access to the previous versions of this course at Northeastern. So I do take some inspiration from my own undergraduate experience, and sometimes I look at problems from other instructors at other universities. But yeah, generally I write the problems or take them from the textbook. There won't be any problems on the exam from the textbook, but. So, good. Any other questions? Good. Right. So we left off Friday discussing how to bound an integral, right? And we went all the way through in computing this example, except for assembling all the components that we derived at the very end, right? So let me just quickly remind you. Right, we wanted to find an upper bound.
Is today's class fair game for the exam? I forget, when is it cut off?
Well, so I'll say this. Right now we're in the midst of exploring techniques of integration, right? Anything that I say today may help you more quickly evaluate an integral. But you will certainly be able to evaluate it with methods that we have discussed before today.
Okay.
Okay?
So there's an integral.
I didn't say that. I said if you have to integrate, you know, you can use whatever we've discussed in class.
So if it was like, I know when we first started integrals, we were talking about like the contour integral over the circle and like how that's used in a bunch of different ways, and then the like ways we can like negate it and stuff. We're totally fine to do it in the same way we learned how to use that. Like anything that we use today is fine. Just like put on and not.
Yeah. Anything we say today is fair to use, but it won't be necessary to appeal to anything that we say today. Yeah. So count this as a extra help for what you might have to do on the exam. Okay, so we wanted to find an upper bound for the modulus of the following integral. The contour integral over gamma of the function e to the z divided by z squared plus 1 dz. Tell you what gamma is, where gamma is a circle of radius 2 traversed once counterclockwise. Okay, so let me just remind you of what we computed on Friday. Recall the length of gamma is just equal to 4 pi, right? The circumference of a circle of radius 2. And we also came up with the bounds that the modulus of e to the z is less than or equal to e to the 2 on the circle. And we also deduced that 1 over the modulus of z squared plus 1 is less than or equal to 1/3 for the modulus of z equals 2, right?
What does gamma of gamma mean?
Oh, sorry, I meant to say length, an upside down gamma. Sorry about that. Right, good. So, altogether, remembering that the modulus function is multiplicative, right? point, we can say that our integral is bound by e squared over 3 times 4 pi. Okay, so again, very often in applications, engineering, sometimes we just need to know that an integral does not exceed some value. So if we can bound our value, then we can know a lot that we care about. And really this just boils down to looking carefully at our integrand, being able to bound that, and computing the length of our contour. Okay? Which is just a fairly standard integral of a single variable, right? Yeah.
Is there any like relevance why that's the volume? Sorry, never mind. It's the 4/3 pi.
Oh, yeah, the complete coincidence.
Yeah.
Complete coincidence that.
E squared, not e cubed.
Right. Yeah. Not a superficial similarity to the volume formula for a sphere, but not really related here. It just happened to come out that way. Okay. So, here's the important takeaway about contour integrals, right? Under the right circumstances, a contour integral does not depend on the actual contour. Just endpoints. Okay? That is to say, when we compute an integral of a real function, the value of that integral depends only on the value of some antiderivative evaluated at the endpoints of the integral. Right? That's the fundamental theorem of calculus. So, what we're saying here is that when we're in a sufficiently nice condition, that's exactly the situation that we're in for a complex function, a contour integral. Okay. So, let's state that precisely. So, let's suppose f of d is continuous in domain d and has explicit antiderivative capital F of z in all of d. What precisely do I mean by that? Just the same thing that I mean in the real case, that the derivative of capital F is just equal to our original function, little f. We're having z in d. Then, what we have for gamma entirely in D, I should say more here, with initial point Zi and terminal point T. We have the following. The integral along gamma of f of z dz is equal to capital F of z sub t, f of z sub t minus capital F of z sub I. Okay, so again, we'll see very shortly that it's critical that we assume that D is a domain, that is to say it's open and connected. Right? This is because this allows us to show that the fact that little f possesses an antiderivative is equivalent to the fact that the integral along any closed curve which is contained entirely in the domain D is 0. Okay. So it, to this point, may have seemed somewhat obsessive to characterize the topological properties of D in such a precise fashion in terms of how we've used it so far. We're about to see why that level of precision is so critical, why that is important to us, even more so than it has been. That's kind of an opinion question, right? Have we been too obsessive about topological properties of D? Maybe not, but it will play a major role, those assumptions of openness and connectedness in what we're about to say throughout the rest of today. Yes?
This is kind of like an analog for conservative vector fields, right? As like closed, or rather, line integrals of conservative vector fields depend only on the end starting and end points.
Right. This is very much an analog of that, right? Of course, we're going to take this a step further because we have this much stronger condition of analyticity, right? We haven't assumed analyticity yet, but we'll be able to say that these integrals behave in a much more regular fashion than integrals of conservative vector fields. When we assume that our function f is analytic, okay? That's where we're headed. That with the additional assumption that f is analytic in D, then we have even nicer ways of computing the integral.
So this is just for f continuous.
That's right. This is just,
Right?
so this is actually quite analogous to line integrals,
Yeah.
right? For conservative vector fields. But what we'll do at the beginning of next week is talk about what happens when f is analytic in addition to B.
You mean lowercase f?
Yes.
Okay.
Right.
That was definitely happening.
Yeah. Sorry. I know this is like classical notation, right? I should say capital or lowercase f. But yeah. So eventually, soon, we'll talk about what happens when little f is analytic, and we'll come up with some nice formulae and bounds in that case. Okay. Okay. So, right. This is really nice, right? Because consider the following thing. Consider gamma given as, we'll just draw a picture of it. Okay, and I'll just draw a picture of it because what this theorem tells me is that I don't have to parameterize this region saying I go up to 2 plus I. Sorry, I guess I should make this somewhat to scale, right? So here's 2 plus I. Here's my contour gamma, right? Everything that we've done so far says that I would have to parameterize the components of this, right? This upper semicircle. I know this isn't very circular, but let's pretend it is a circle. And this line, and then break my contour integral up over gamma of these two regions. Okay, so here's my gamma, and let's suppose we want to compute the integral along gamma of cosine of z dz. Okay, so everything that we've said so far would require us to parameterize the two smooth pieces of this contour, and then plug that parameterization into cosine, and then multiply by the derivative of that parameterization, and then evaluate on each smooth piece, right? Okay, but in light of this theorem, right, I know that sine of z is an antiderivative of cosine in the entire plane, right? So I know that this is just sine of 2 plus I minus sine of -1. Okay? No parameterization necessary. Okay? Which, as I said, we get by pretty fine with everything we wanted to discuss, just parameterizing circular arcs and line segments. So it's not that bad, but it is quite a bit more computation that we have to do, right? And now, with this theorem, if I can produce an antiderivative, I can simplify the problem greatly. Okay? So, right. Let's prove this theorem. So, let's suppose gamma a contour in D. Joining the initial point to the terminal point. Okay? And let's select a smooth parameterization of gamma z going from the interval a to b into the complex numbers. Okay, so really what I mean by this, if I want to actually prove this in full generality, I'm assuming that gamma is a sum of a finite number of smooth directed curves, right? So when I say select the smooth parameterization, what I mean is this z is piecewise smooth, right, for each component of gamma. Okay? So let me write that down. Meaning, how should I write this? Z of t is equal to z sub 1 of t for t between a and t1, or tau 1, I should say. C2 of t for t between tau 1 and tau 2. The n of t for t between tau n minus 1 and b, right? Where gamma is consisting of these n smooth directed components, little gamma 1 through little gamma n. So, right. Then the integral of f of z dz along gamma is equal to, just by definition, the sum of the integrals along gamma j of f of z. I guess I'll do this. F of z dz, which of course by our main theorem that we use to evaluate integrals, I can on each component plug in these piecewise smooth pieces of my parameterization and tack on the derivative. Right? This is the sum from j equals 1 to n of the integral from tau sub j minus 1 to tau sub j of f of z sub j of t times z sub j prime of t dt. Okay. So now we're in the case of a real function, right? A function of a real variable. So we can apply the fundamental theorem of calculus, right? That is to say, we were assuming that f has this antiderivative in d, right? So we can evaluate each of these integrals using the fundamental theorem of calculus for real valued functions, right? Okay, so this altogether is equal to the sum from j equals 1 to n of the antiderivative f of z of tau sub j minus the antiderivative of f z sub, z sub j, right? Z sub j. J. Of tau sub j minus 1. Okay, now this is just a telescoping sum, right? That is to say, oh, actually, I'm sorry. I don't need this j, right? I just assume that I use the correct piece of j, of z, for each tau. right? I don't have to put that additional subscript in. That's superfluous. And it kind of obscures my point, right? That, remember, the pieces of my contour gamma line up at the endpoints, right? So that is to say, for example, z sub 1 of tau sub 1 is equal to z sub 2 of tau sub 1, right? So the point is that I cancel all my terms except the very last term and the very beginning term in this sum, right? That is to say, this results in f of z of tau sub n minus f of z of tau, sorry, not t, tau sub 0. Okay, I didn't say this, but here I started my tau as 1. What's tau sub 0? That's just A, yeah. And what's tau sub n? It's just B. Right? So, f of z of A, oh, I'm sorry, B, minus f of z of A. Now, remember, I assumed that the endpoints of my contour were z sub I and z sub t, right? Capital gamma goes from z sub I to z sub t. That means that z, the parameterization of B, is just z sub t, right? And likewise, for z of A, the parameterization z evaluated at A is the initial point of the contour gamma. So there you have it. This is our analog of fundamental theorem calculus. Right? Now, just a side note here. Again, it will become more and more important, the property that D is a domain, but remember here that our antiderivative f has to be an antiderivative for lowercase f in all of our domain, right? So think about log of z, right? This serves as an antiderivative of 1 over z, right? In the domain d star, which is the slit plane, right? We take out the negative real axis, or I'm sorry, the non-positive real axis. So that is to say, if our contour crosses the negative real axis at any point that we would like to integrate against, then we have to choose some other branch of log z as an antiderivative of 1 over z to integrate that. Okay? So it might seem pretty innocuous. Like, what I've said formally here looks just like the fundamental theorem of calculus, but we've actually built this to be quite a bit more complicated, because we're saying this depends on the antiderivative existing in D, some domain that we have.
So if you had a gamma that was like a circle, it wouldn't be possible because there's no branch cut that doesn't have its slit going through them.
Yeah, right. So, well, actually, there's some clever trick that you can do to do something about that we'll discuss in a week or two. but I'm glad you think of that. Yeah, so what kind of domain can we define that excludes just, or what kind of contours can we integrate in that behave kind of like a circle, but avoid the negative or the non-positive real axis? Kind of like a, I'll draw this now, and then we'll talk more about it later. Do something like that, like a Pac-Man contour. We want to do something like a disk for the case of integrating 1 over z in some disk-like thing. Okay, so we'll talk about this at great length in a short while. That's good. I'm glad you're thinking of this. Yeah.
Thinking back to last class, when we were talking about the contour integral of the circle of like that g minus z naught to the n. The reason why, so we have to assume for this condition to be true that f has to be continuous in domain D. And for the case that n is equal to -1, it's not continuous everywhere because it's not continuous at that point z equal to z naught.
At Cole? Yep.
Yeah, so that's why we can't just apply this theorem like we were doing for all the positive.
Yeah.
Yeah.
Yeah, that's right. And I also said that that example was somewhat typical. Right? We'll see how we can use that example to characterize what happens when our the function that we're integrating is non-analytic at a finite number of points. We can still compute the integral in a very regular fashion. If it's not analytic at a finite number of isolated points, right?
Is it some multiple of 2 pi I?
We'll have to see.
So even though for any negative n, it isn't defined at z naught, it's only n is -1 that you get a unique answer.
Right. So the story's a little more complicated, right? We have to do some work to understand why that is.
So all the other negative n's, you can't do the process that we just did, but it still ends up being the same answer for as if you had done it for positive n.
Well, I'll just ask you to hold that question in mind over the next several sessions that we have. But this is a good line of thinking that you all are progressing. I don't want to.
This theorem requires that the n continuous. And so when we got the -1 for the n and the other one the n, even though the function is continuous over R gamma.
That's definitely part of the story, right? You know, you can define some antiderivative, but it will still be discontinuous when n is less than -1, right? Yeah, so good. Remember all this over the course of the next week and a half. Okay? Okay, so for now, let us content ourselves to continue to build towards these facts which you're using. If f is continuous in domain D, and has antiderivative in all of D, then for any loop gamma lying in D, the contour integral along gamma of f of z dz is equal to 0. Okay? A loop being a a function which has its initial and terminal points coincide. And that's just directly from this formula. Okay.
Do we ever write the closed loop symbol from the integral, or is that not something we do in complex variables?
I think it's clear what you mean if you write that. If you so prefer to write that, you can. It might make a scant appearance in the textbook, but whatever you like. Okay. So let's put all this together, and what I'm about to write down might seem highly non-useful, but the next portion of our work will give us an effective means of checking these equivalent conditions I'm about to write down. Okay? So, again, we'll assume if f is continuous in D, the following are equivalent.
Is D not the domain? Or is it just...
Oh yeah, D
Okay.
as we've said before, is a domain. I was just being lazy here.
That's what I thought. I just wanted to make sure.
Yeah, no, good.
And when we say domain, we mean an open connected.
In the topological sense, yeah, an open and connected planar set. Good. Okay, so the following three things are equivalent if f is continuous in a domain. F has an antiderivative. Okay, one word here. Remember that a function being integrable does not imply that it has an antiderivative, right? That just means that in some domain, the limit that defines the integral exists for each value that you can take in that domain, right? Think back to, maybe you've seen this in calculus too. What's the antiderivative of e to the negative x squared?
Over the whole domain.
What's the antiderivative anywhere of e to the negative x squared?
The Gaussian function.
Well, so that it is the probability density function for a Gaussian distribution, but it has no elementary
Yeah.
antiderivative, right? Yet you can numerically approximate the integral, right? That is to say, it's integrable, but has no antiderivative. Okay? So this is not, we're not saying a trivial thing here, right? Just because f is continuous, yes, it's integrable in D, but possessing an antiderivative is an extra condition that we're asserting that f has. Yeah?
Just a question. When we say like something does not have an antiderivative, does that mean it doesn't have an antiderivative that can be written in terms of elementary functions?
Yeah, that's what I said, that it doesn't possess an elementary antiderivative.
Okay.
Yeah. So, of course, you can, what is the definition of a function?
Yeah,
Well,
you
you
can find it a
just,
certain way.
you just say what the value is for each input value. So you could hypothetically say some way of generating,
Yeah.
but yeah, not a formula that we can manipulate in the standard way that we would think of manipulating a function, right? Okay. So, this is equivalent to every loop in the domain D. Let's call it gamma, any loop, has the contour integral along gamma of f of z dz is equal to 0. We kind of just said that in our corollary, right? We've already shown 1 implies 2. This is also equivalent to the fact that the contour integrals of f along any contour entirely in D are path independent. Well, okay, we've also already seen that 1 implies 3. Right? Just by this last statement from our last theorem. So, really, all I have to do is show that 2 implies 3 and 3 implies 1. Right? Show that these are logically equivalent. That is to say, we can construct an antiderivative for the function f, little f, if we know that the contour integrals along f are path independent for any contour in D, which, when I say it that way, is maybe a little bit surprising, right? How do we construct a function out of this? I guess it's time to take a break. Let's reconvene in 5 minutes. You can prove this if you don't have anything better to do. I'm gonna wash my hands. Oh yeah, I remembered one of the other things that another topic. Of course, like I said, I'll write all this down and send it to you. Maybe somebody would be interested in talking about analytic continuation, which is if you're given some function which is analytic in some domain D, you might ask the question, what is the largest domain I can extend that function in a way that is analytic, that agrees with the original function values on D? And what's the biggest open set that I can find that contains D? where I can define a function that agrees with my original function on the original values of D, which is analytic in the larger domain. And this has some connections with how one formulates the Riemann hypothesis, which is extremely interesting. Right, so I'll include that on the list. Yeah. You know, looking at the amount of time that we have left and where I tend to get, I'm baffled at how we did as much as we did when I was an undergraduate. I don't know how we moved so fast. I hope that nothing feels too rushed so far for us. Yeah, we should be able to get to the point where we begin to discuss we'll go through most of chapter 6 of the textbook, I think, by the time we finish in time for everybody to give their presentation.
Bless you.
Thank you.
Okay, so I guess we should start again. Let's just demonstrate how 2 implies 3 and 3 implies 1. We're pretty convinced, I think, of 1 implying both 2 and 3. Maybe I could do slightly less work, but I think it's worth showing how these things are related. Okay, so here's our proof. We'll assume 2, right? And let's let gamma 1 and gamma 2 be any contours in D that share initial and terminal points. Okay, so here's a schematic diagram. Here's my domain D. Let me have my initial point here, Zi, and my terminal point here, Zt. Here's gamma 1. And remember, contours have direction. Here's gamma 2. Say it has this direction. They share initial and terminal points. Okay? So, then let's set gamma equal to gamma 1 plus the negative of gamma 2. That is gamma 2 with the opposite orientation. Okay. Then the integral over gamma, or along gamma, of f of z dz, just by definition, is equal to the integral along gamma 1 of f of z dz, plus the integral of negative gamma 2 along negative gamma 2 of f of z dz is equal to again, the integral along gamma 1 of f of z dz minus the integral along gamma 2 of f of z dz. But remember, we're assuming condition number 2, that the integral around any closed loop in D is 0. So we know that this integral, so everything I did up to saying this is equal to 0 is just smooth contour arithmetic, right? And then I know that this is equal to 0 because I'm assuming part 2, that the integral around any closed curve, which is what I get by traversing gamma and then the negative of gamma 2, traversing gamma 1 and then the negative of gamma 2, must be 0, right? So this is to say the integral along gamma 1 of f of z dz is equal to the integral along gamma 2 of f of z dz. Okay, that is to say, even in the absence, I haven't assumed anything about the existence of an antiderivative of f, but yet I have shown that in some way that this integral depends only on the endpoints, right? Zi and zt. Okay, I haven't made that dependence explicit because I haven't assumed that an antiderivative exists or shown that one exists. But it doesn't matter how I get from Zi to Zt, as long as I stay in D to do it. Okay, good. And I guess I should say, so this implies that part 3 is true, right? Okay, so now let's assume 3 and show 1, right? That is to say, we want to construct an antiderivative for the function f, assuming that our integrals are path independent. Okay? So, let us fix some point Z naught in D. Yeah? Then for any other point Z in D, set the value of the integral. Well, actually, let me say this in a different order than I have it written down. We might make more sense this way. Let gamma be any contour in D connecting Z naught to Z. Okay? Then what we'll do is we'll set this value, capital F of Z, equal to the contour integral along gamma of little f of w dw. Okay? That is to say, I'm making a definition. Okay? It doesn't matter what gamma is, what the contour gamma is, as long as it remains in D and connects Z naught to Z. Okay? And when I compute the contour integral along gamma, I get some complex number. Right? So this right-hand side is some complex number. And I'm just giving it this name, capital F of Z. Okay? And my intention is to show that this defines a function, and that in fact, this function serves as the antiderivative of little f. Okay? So, first of all, how do I know that such a contour, gamma, exists in D?
It's open connected.
Because it's connected, yeah, because D is connected. And remember, my condition for being connected is that any 2 points can be, you can draw a polygonal path between those 2 points, which is contained in the set. Okay? So that is to say, we know such gamma exists since D is connected. Take gamma to be a polygonal path. Okay, good. Just being very precise here, right? Okay. So what this tells me is that f of z is a well-defined single-valued function. Well-defined because I can always find a path gamma. Right? I can always find a contour gamma. Single-valued because we're assuming 3, that the integral is path independent. It doesn't matter what gamma we chose. The fact that we can find one suffices to say that there is a single value for each z, for f of z. Okay. So, now we demonstrate that f prime of z is equal to little f of z. Okay, so, right. To do this, let's compute f of z plus delta z minus f of z. Okay. Right, so, how will we do this? First, by, computing, f of z plus delta z along contour gamma connecting Z naught to Z, then the line segment L from to Z plus delta Z. Okay, let's let me draw you a typical situation. Okay, right, so here's some domain D, right, an open and connected set. We'll say here's my fixed point, Z naught, and here's Z. Okay, so doesn't really matter what I do, however I want to get there, but as long as I stay in D, say here's my contour gamma. Okay, and then I'll go this additional little line segment length from Z to Z plus delta Z. Right? Just a tiny little change in Z. This is, of course, I've made some arbitrary choices in drawing this picture, right? But it is the typical situation, essentially. Okay? So the thing to notice here is L must lie in D when delta Z is small enough. Why is that?
It's open.
Because it's open. Yeah. That is to say, remember, we know that the point Z is in D, which means there's some open ball around Z, which is contained entirely in D. So as long as delta Z is smaller than the radius of that ball that is contained in D, centered at Z, then I know that this line segment L has to be entirely in D, or small enough delta Z. And of course, you probably already have the intuition that delta Z is this thing that we're going to let go to zero, right? Because we're computing a derivative. We're looking at an infinitesimal change in the end. Okay? Since D is open. Okay, so putting this all together, what we get is that, oh, sorry, I should say before, I forgot an ingredient. Let's parameterize L by Z of T is equal to Z plus T times delta Z, for T between 0 and 1. Okay? Remember, we know how to parameterize line segments. Here's one such example of how to parameterize L. Yeah? Okay, so putting this all together, we can go back to trying to compute this value, right? This is, for example, equal to gamma plus L of f of z, sorry, f of w, right, my dummy variable, dw, minus the integral along the contour gamma of f of w dw. Okay, then again by my standard integral arithmetic, right, I have the integral along gamma of f of w dw plus the integral along L of f of w dw minus the integral along gamma of f of w dw. Okay, now we'll use our main tool that we have so far and plug in the parameterization that we produced of L, right? So that is to say we resolve this to the integral from 0 to 1 of f of z plus t times delta z times the derivative of this parameterization with respect to t, which is what? It's just delta z. Okay, which of course is a constant with respect to t. Which is to say this difference quotient is equal to the integral from 0 to 1 of f of z plus t delta z dt, right? Oh, we're getting pretty close. What happens when we take the limit on both sides of this as delta z goes to 0? What do we have? We have limit as delta z goes to 0 of f of z plus delta z minus f of z divided by delta z is equal to, what happens here when I let delta z go to 0?
F of z dt.
Yeah, right. Which is just a constant with respect to t, right? So when I perform this integral, what do I get?
F of z.
I just get f of z, right? So everything that you said is valid there because f is continuous. Continuous functions, well, another way to characterize continuity is that they commute with limits, right? You can take a limit of the argument is equal to a limit of the output of the function. Okay. So let me just say that since f is continuous, so altogether, what does this tell us? Now we just recognize the limit as the definition of the derivative for capital F, right? So in fact, this function that we constructed is the antiderivative of lowercase f. Okay, it's I think we all agreed at the outset that it was somewhat surprising that we could construct an antiderivative, given this information that the integral is path independent, right? But it turns out that we actually just use the expected formula to define some function, right? We build a function that must satisfy the formula that we want. Yeah.
Just one clarification. So in the first line on the top of the left board, how do you get from the integral along little l fw dw to the integral from 0 to 1 of f of z plus t delta z delta?
This one?
Yeah. Yep.
So this is, remember, we had this theorem on Friday, where if you parameterize a contour, or a smooth directed curve, and you want to compute the integral along that curve of some continuous function along that curve,
Oh, yeah.
you just plug in the parameterization and then multiply by the derivative.
It's more the question of, so just w is a dummy variable, so we just substitute for z of t, right?
Yeah.
Okay, that's
WT, Z of T, whatever you want, you know. Yeah, it's just because, like, if I had put Z here, that would have been even more confusing, right? I'm just parameterizing the input of F, whatever it is, as an integrand. Okay. Good. Okay, so if we're trying to come up with conditions for an antiderivative to exist, it might appear that I've said something quite useless, right? I've said, well, okay, I can construct an antiderivative if I know that the contour integral along any closed loop is 0. That is to say, it seems like I would have to check every closed loop in some domain D in order to guarantee that I can construct an antiderivative. And that doesn't seem very effective, right? But in fact, we will see, thanks to something I learned, it was called the Cauchy-Goursat theorem. The textbook calls it the Cauchy integral theorem, but does mention Goursat in the footnotes. I don't know why the downgrade happened, but let us call it the Cauchy-Goursat theorem. The Cauchy-Goursat theorem gives us an effective condition for the existence of an antiderivative. And it depends on this notion of continuous deformation of a loop. That is to say, we want to be able to take some loop in a domain D and move it around in a continuous fashion so that we get to some other loop. Right? We say these are continuously deformable into one another. So we're going to spend some time making precise exactly what that notion is. How we characterize curves which are continuously deformable into one another. And this is actually, so let me give you the definition and then I'll make some remarks. This could actually be a final project discussing what the implications of this notion of continuous deformation actually is. Okay, so here's the definition. Okay, so a loop gamma naught in domain D, again domain, our topological definition of domain, is continuously deformable a loop gamma 1 in D if there exists a continuous function z of s comma t of two variables on the unit square What do I mean by the unit square? I mean that our two variables, s and t, both run between 0 and 1. Okay? Satisfying three conditions. 1. For s between 0 and 1. Function z sub s of t, which I may sometimes write z sub s of t. Parameterizes a loop in D. Okay, so what am I saying here? I'm saying for any particular s, for any real number between 0 and 1, I plug that into z of s comma t. That's why I might sometimes turn it into a subscript when I'm looking at a particular s, right? To make it clear the notion that I'm picking a particular s. Okay? Really, this is a variable of the function z of s comma t, but when I pick a particular one, I may choose to denote it this way, just to make the distinction. Okay? Right, so, and then kind of what you would expect that z naught of t parameterizes gamma naught and z1 of t parameterizes gamma 1. So let's just take stock of what we've said here. We're parameterizing a family of parameterizations. Okay? That is, for each value s that we put in, we're parameterizing some curve. Right? And s is a parameter of this family of curves. Okay? And we do this in a continuous fashion. Okay, so here's what I wanted to say, the possibility of this being a project. This is called, sometimes instead of continuous deformations, this is called homotopy, which is a very difficult and fine classification of different classes of topological spaces, right? You can extend this to arbitrary dimensions, right? The notion of a continuous function is quite general, right? Of course, how we've used it in the term so far, it's been the kind of familiar notion of continuity that we talk about all the time in calculus. But essentially, the spirit of this definition gives you a way to come up with a classification of which topological spaces are the same in some fairly fine division. And by fine, I mean there are many different classes. So, again, I'm gonna record all this, but I feel like I can't remember everything. So when you look, you might look back at your notes and see some of the things I said. So let's just say, homotopy, the topological application of its definition. It's possibly a good topic for a final project. Seeing the general definition of homotopy and how that relates to homotopy of closed loops, as what we're concerned with. Okay? Okay, so let's just look at some examples of what this continuous deformation notion kind of looks like. Okay, so let's take our domain is some open annulus, yeah? And we'll take a loop gamma naught. And further out here, we'll take the loop gamma 1. A continuous deformation is, for example, the family of circles with the same orientation with increasing radius until I get out to the radius of gamma 1. And I start at the radius of whatever gamma naught has, and I move out to the radius. That is to say, for each value of s, I have a successively larger and larger radius, until I get to s equals 1, and then I have the radius of gamma 1. Okay? So, remember, we're only concerned with continuity here, not smoothness. So I could even take the same domain D, right? For clarity, I won't fill it in with stripes, just so you can see what's going on with the curves more. And let's say I take this polygonal contour. We'll call this gamma naught. I can continuously deform this into a circle, gamma 1. I didn't put an orientation on this quadrilateral. But, so what's my continuous deformation here? Well, I move from this quadrilateral to something, maybe it's a little more curved around the edges. It's not as sharp. And so on, right? I just think of a contour as like a rubber band, right? And I can just kind of stretch it, pull it to make it into some other shape. And those shapes that I can just pull it into are the ones that are continuously deformable from the shape that I start with, the contour that I start with. Okay. Now, here's perhaps a slightly more interesting example. Let me itemize these, I suppose. What if I asked you, is it possible, let's take as my domain D the entire plane, just this section of the plane right near where I am, say. Okay? Let's say here's gamma naught. gamma 1, circle with the opposite orientation, translated over. Can I continuously deform gamma naught into gamma 1? Can I hear no?
Could you reflect it over some arbitrary axis?
Is a reflection continuous? I think if you actually take the time to write out an equation for a reflection, you'll see that it's not continuous in this setting. I'm fairly certain that's the case. Good idea though. There's something else we can do without leaving the plane. And that's kind of the problem. We want to stay within our domain D. And to reflect, we would have to kind of like move out of the plane. Yeah.
Well, we can just smoosh it into a line and then expand the other way, right?
Yeah, that's almost exactly right. We want to compress it down into something that has less dimension. Okay? So instead of a line, we're actually just going to shrink it down to a point. Because remember, we allow contours to be points. And here, direction has no meaning. Right? If you're just staying at a single point the entire time you're parameterizing something, there's no direction to speak of. So that's exactly what we'll do. We'll say like we'll become smaller and smaller, and then we'll just become a point. Let's say if we parameterize this nicely, we could call this contour gamma 1/2. Halfway through, we're a point. Okay? And then when direction has no meaning, we can assign it the opposite direction without consequence. Okay? And then we'll start to get bigger and bigger with the opposite orientation until we get to gamma 1. So this is continuous, surprisingly enough. Good.
Could you give an example of one that is not continuous, a loop that is not continuously deformable?
Yeah, let's do that now. Okay, let's let our domain now be the complex numbers minus plus and minus I. Okay, so here's a little schematic of my plane. Here's I, and here's minus I. So if I start with some contour, gamma naught, I can continuously deform this down to a barbell shape. So yeah, I can continuously deform this down to gamma 1, but here's what I can't do. I cannot deform this into gamma 2. Okay, so gamma naught to gamma 1, all I've done is I stay in my domain if I shrink this down and have a line connecting my two pieces of this contour. However, I can't continuously deform gamma naught into gamma 2 because at some point I would have had to contain the point negative I. Since negative I is not on the inside of gamma 2. Okay? So we've been thinking about this in kind of a discrete fashion, right? I draw this type of picture for you. I drew just 2 steps, then a middle step, and then 2 steps to the final step. But it has continuum many steps, right? So somewhere, if I try to deform gamma naught to gamma 2, somewhere one of those curves, one of those values of s would result in a parameterized curve that passes through negative I. And therefore I would have gone outside my domain. Remember condition 1. For each s, we parameterize a curve entirely in D. Okay? So, this is the backbone of how we will be able to effectively produce antiderivatives for given contours, contour integrals. Okay? We'll talk more about that on Monday. So I'll send out the solutions to the practice exam this evening. And feel free to email me with any questions. You don't have to wait till office hours. Have a good afternoon, and I'll see you on Friday.
Thank you.
Mhm.